Welcome to this session. Today we are going to discuss Vertex Degree and Handshaking Property for graphs, that is undirected graphs. What is a Vertex Degree? The number of edges connected to V, vertex V, is known as the degree of that vertex, and it is denoted by degree of V. It is denoted by degree of V. See the number of vertices. Suppose if I am going to consider a graph is like this. So if I am taking a graph is simple graph is like this. So here V1, V2, V3, V4. So how many edges are connected to this vertex? So the number of edges connected to V is known as the degree of vertex. So degree of V1 is 3, degree of V2 is 2, degree of V4 is 3, degree of V3 is 2, like that. So that is going to be represented as a degree of V. Either we can represent capital D or small d also we can represent degree of V. Now, suppose if I am going to consider any directed graph, earlier previous sessions, we know that in a directed graph, if there are two degrees will be there. One is in degree and one is out degree. That means for every edge you are going to consider, so it is having one in degree and one out degree. So that we discussed already in the previous sessions. Now, for any loop if you are going to consider, suppose I am just taking one loop is, let us say V3 is having one loop, then it contributes degree 2 of that particular vertex. So here degree of V3 is equals to 4 we are going to take. This is for 2. One is incoming and one is outgoing. For that like that we have to consider. So it is 2 and then the remaining also 2 edges are moving that. So degree of V3 is 4. And suppose if any vertex if I am going to consider, let us say another one is V5 here, V5, then it is an isolated vertex because it is not connected to any one of the vertex. So then the degree of this vertex is 0. Degree of vertex is 0. Suppose if I am going to consider, let us say another one is V6 is there, V6 is there, and V4 is connected to, let us say, V4 is connected to V6. Then, so this is a pendant vertex. So then that means from this it is not going to be connected to any one. So now V6 degree is 1. V6 degree is 1 and the corresponding edge we are going to take it as a pendant edge. Let us say E1. V4 to V6. So V6 degree is V6 is a pendant vertex because then in such a case the degree of that vertex is 1. And then the corresponding, that means the edge is incident to the pendant vertex, which is known as a pendant edge. So E1 is known as a pendant edge. Now let us go one of the property, that is handshaking property. So here the sum of the degrees of all vertices, must be equals to of a given graph is equal to the even number, and it should be equal to the number of 2 into the number of edges. 2 into the number of edges. So here the sum of the degrees of all vertices in a graph must be an even number, and this number is equal to twice of the edges of the graph. That we are going to equivalently written as the alternate form of this is we are going to consider this. That is the sum of the degrees of all vertices must be even, and that should be equal to 2 into the number of edges. So that we are going to represent like this. And now here the proof of this is very simple. That means since degree of a vertex is the number of edges incident to that vertex, so the sum of the degree counts the total number of the times of an edge incident to that incident to with a vertex. Since every edge is incident with exactly two vertices, that means any edge if I am going to consider. So let us say I am just taking one edge if I am taking. So it is a V1, it is moving from V1 and of course V2, whatever that is incident to V1 and it is incident to V2. That means each edge is counted twice. Each edge is counted twice. So whatever the number of edges, whether the number of edges are odd or even, it should be multiplied with twice. Subsequently, we can get only even number. Subsequently, we can get the even number. So that's what we are going to say. This is one of a simple property that is known as handshaking property. Now we are going to discuss some of the problems which are related to the handshaking property. Now here, in a simple graph G, which is having 24 edges and each vertex degree is 4. Find how many number of vertices it is having. How many number of vertices it is having. So let us consider the graph is having n number of vertices. N number of vertices. And each and every vertex degree is 4. It is given. So the total number of the sum of the degrees of all vertices. So it is a degree of all vertices. So whatever the vertices will be there, this we are going to consider it as each vertex degree is 4. Then the sum is 4n. The sum is 4n. And now the sum is equals to sum of the degrees of all vertices must be equal to 2 into number of edges. How many number of edges? It is given as 24. So it is a sum of summation of dvi, degree of the vertices, I is equals to 1 to n. I is equals to 1 to n is equals to 4n. So we are going to take it as 4n. And this is nothing but 2 into number of edges. So from this, I can get 2 into 24. So from this, there are 12 number of vertices will be there in that graph. So here, the assumption is number of vertices is equals to n. Then that n value we are going to calculate it by using the handshaking property. Now, let us go for the other example. A graph is consisting 21 edges. 21 edges. So it is given m is equals to 21. Number of edges is equals to 21. And 3 vertices of degree 4 and other vertices of degree 2. Then find the total number of vertices. How many number of vertices it is having. So here it is given the total, the number of vertices of degree 4 is 3 and remaining vertices degrees are 2. So here let us assume that the graph is having n number of vertices. So if it is n number of vertices will be there, so n minus 2 vertices, n minus 3 vertices is of degree n minus 3 vertices of degree 2 and 3 vertices of degree 4. What is the sum of these degrees of these vertices? 2 into then n minus 3. And what about this sum is 3 into 4, so which is equals to 12. So the sum of the degrees of vertices is 2 into n minus 3 plus 12 plus 12. That's what we are written here. So it is nothing but 2 into, then it is, this is 2 into n minus 3 plus 12 is equals to 2 into number of edges. This is the handshaking property. So number of edges is 21. So it is from this we are going to calculate how many number of vertices it is having, which is equals to 2 into number of edges is 21. So from this we can calculate what is the number of vertices in that graph is having. So n is equals to 18. Now let us go for the other example. A simple graph which is having 35 edges. Number of edges are 35. And 4 vertices of degree 5. 4 vertices of degree 5. 5 vertices of degree 4. And 4 vertices of degree 3. Find the number of vertices of degree 2. Find the number of vertices of degree 2. See 4 vertices. 4 vertices. This is this we are going to consider it as, see, 4 vertices. These are I am taking vertices and these are degrees. So 4 vertices, degree is 5, and 5 vertices, degree is 4, and 4 vertices, degree is 3, and find the number of vertices whose degree is 2. Whose degree is 2. So let us consider the number of vertices of degree is 2. Of degree is 2 is n. We are taking. Let us consider the number of degree 2 vertices of the given graph is n. Of the given graph is n. Then what is the this is the handshaking property. Then what is the total sum of the degrees of vertices? This is 4 into 5 plus 5 into 4. Then this is a plus 4 into 3 and then plus 2 into n. This is the total number of sum of the degrees of vertices. So here it is, what is this? 4 vertices, sum is 4 into 5. Each vertex degree is 5. So 20. So here the sum is 5 into 4. This is also 20. And this is 4 into 3. So it is 12. So it is from n vertices of degree 2. So it is 2 into n. 2 into n. So that we are going to consider the sum of the degrees of all vertices is equals to this one. Now which is equals to 2 into number of edges. So it is nothing but 2 into number of edges is 35. So this is equals to the sum we have to write here. The sum is writing here. Then that is equals to, see here we are written, everything is like here. And then, and we are going to calculate what is the n. N is nothing but how many number of vertices will be there in the graph of degree 2. So there are 9 vertices. 9 vertices are there of degree 2. Of degree 2. Now let us go for other example. Now a graph which is having 24 edges. Graph having 24 edges, and each degree of each vertex is k. Degree of each vertex is k. Then which is the possible number of vertices? So here there are number of vertices are not given. So each and every vertex's degree is given. So now we are going to consider number of vertices are n. Number of vertices of the given graph is n. Now each and every vertex degree is k. Then there are n vertices will be there. Then what is the total sum of the degrees of vertices? Which is equals to n into k. Which is equals to n into k. Which is equals to 2 into number of edges by handshaking property. So it is 2 into 24. Then k I am going to get like this. K is equals to then 48 by n. So here then which is possible number of vertices? What is the order? What is the order that we have to calculate? Then I am going to simplify this. I am going to take the n, we are going to get a whole number. N we are going to get a whole number. For k is equals to, we are going to get a whole number, because the degree should be, it should not be a fraction. It should not be a fraction. It should be a whole number. It should be a whole number. So for what value of n, we are going to get a whole number. We are going to get a whole number that we are going to calculate from this. So here, just to trial and error, I am going to take some of the numbers which are going to be divisible by n. So for that, we are going to take it as n is equals to 8. N is equals to 8. Then it is going to be divisible. 48 is divisible by n is equals to 6. N is equal to 8. So I am going to take n is equals to 8. See here, n is equal to 20. If I am taking fraction, I am getting. N is equals to 10. I am taking another fraction. I am getting. N is equals to 15. I am taking another fraction will be there. See, if I am taking fractions, will not be allowed, because the degree should be a whole number. Degree should be whole number. So for n is equal to 8, I am getting a whole number. I am getting a whole number. So for that reason, I am going to take it as k is equals to, that means k is nothing but the each and every vertex degree is 6, and it is possible for n is equal to 8. N is equals to 8. So the number of vertices must be 8. Must be 8. Now we are going to verify the handshaking property for any graph is given. Then this is the graph is given. Now we are going to verify. That is nothing but the any graph if we are going to consider, and whether the graph is satisfying the handshaking property or not. For that, just we are going to verify what is the degree of A. Degree of each and every vertex. Degree of A is 3. How many edges are moving from that? It is only 3. And the degree of B is, degree of the other vertex B is equals to 2. So I am taking 2. Degree of C is 3. Degree of D is 2. Degree of E is 1, 2, 3, 4. Degree of E is 4. And the degree of F is only 2. Degree of F is only 2. Now, sum of the degrees of all vertices, if I am going to add all the things, then I am going to get 16. So this is equals to 2 into number of edges. How many edges it is having? 1, 2, 3, 4, 5, 6, 7, 8. So which is nothing but 2 into 8, and the graph is having 8 edges. So I am going to write this like this. So this is nothing but sum of the degrees of all vertices. So let us say in general, I is equals to 1 to n. This is the generalized way. Then that is even number, and it should be equal to 2 into number of edges of the graph. So it is nothing but t. And now let us go for the other example. I am just taking one more example. Let us take vertex A, which is having a self loop, and then it is connected to, let us say, another vertex C. Then this I am going to take it as connected to B, then it is connected to D, and then it is like this. And of course there is a isolated vertex will be there, E, and then I am going to connect to another vertex F, then which is going to be connected to Z, and which is going to be connected to H. See, we are going to verify once again what is the handshaking property verification, that we are going to do this. So for this graph, verification of handshaking property. So now, what is the degree of A is? Degree of A is. So what is the degree? Self loop will be there. That we have to consider degree as 2. So 2, and then this is 3. And then degree of B is equals to, degree of B is only 2. And then degree of C is equals to, degree of C is equals to 1, 2, 3, 4. So it is 4. Then degree of vertex D. So I am just taking, let us say this is both are same. I am taking that. Degree of vertex D is only 2. And the next degree of vertex E. So E is, there is no edge is passing through that. It is isolated. So I am taking it as 0. Then degree of F is 2, and the degree of G is equals to 2, and the degree of H, which is a pendant vertex, so it is 1. Now what is the total degrees are? Degree of 1, 3, 2, 6, 5, 9, 10, 10, 16. So the sum of the degrees of all vertices, okay, which is equals to, let us say I am taking Vi. I is equals to 1 to n. So 1 to, what is that? 1, 2, 3, 4, 5, 6, 7, 8. 8 vertices. Then it is equals to 5 and 9, 10, 16. So which is equals to 2 into 8. So what about how many edges it is having? 1, 2, 3, 4, 5, 6, 7, 8. See, 1, 2, 3, 4, 5, 6, 7, 8. So it is nothing but 2 into number of edges. 2 into number of edges. So this is the way that we are going to verify the handshaking property. Then next another one is, in theorem. In every graph, the number of vertices of odd degree is even. In every graph, the number of vertices of odd degree. Suppose if you are going to consider what is the odd degree here, this is the odd degree. So vertex A is there with odd degree, one vertex, and another vertex is C is there, let us say, then C is there, this is another vertex, odd degree. I am just saying odd degree vertex. So then the another one is 1, 2, 3, 4 and another one is 1, 2, the remaining are there. So here how many odd degree vertices are there? 2. Odd degree vertices must be even. That is the theorem of the statement. In every graph, the number of vertices of odd degree is even. In any graph, if you are going to consider, each and every vertex degree is either even or odd. In that, we have to count the number of odd degree vertices. That should be even. That is the statement says. Now, we are going to consider a graph which is having n number of vertices. So, in this n number of vertices, some of the vertices degrees are odd and some of the vertices degrees are even. So, we are going to take whatever the odd degree vertices will be there. I am going to take all the odd degree vertices from the beginning and even number of vertices I am taking at the end. Without loss of generality, I am going to consider first k vertices are of odd degree. Just I am going to rearrange the odd degrees wherever the odd degrees will be there. Those odd degrees I am going to take first odd degrees I am going to pulling in one side and the remaining even degrees. So this is odd degree vertices and this is even degree vertices. Let us assume that the odd number of degrees are let us k be the number of vertices whose degree is odd, and we are going to take it as the total number of vertices are n. Then the remaining are n minus k vertices are of even degree. So let us assume that the k number of vertices whose degree is odd, those we are going to consider V1, V2 and so on, Vk. V1, V2 and so on, Vk. So here I am just taking the odd degree vertices are V1, V2 and so on, Vk. The remaining vertices, let us say Vk plus 1, Vk plus 2 and so on, Vn are considered as degrees of even. Now, the sum of the degrees of all vertices can be written as k equals to 1 to n. Then I am going to take it as up to here. I am going to split this from here and then from here to here. So we are going to consider degree of Vi. I is equals to 1 to k. Then here this is I is equals to k plus 1 to n. I am going to take it as I is equals to 1. I is equals to 1 to. Then this is I is equals to k plus 1 to n degrees of Vi. So the whole thing is I am going to split into two parts. One is a k vertices and n minus k. Subsequently, it will become the given. Let us assume that this is equation 1. Now, by handshaking property, what it says that it should be total should be even. So this should be even. That means whatever the degree that I am going to consider, I is equal to 1 to k. What I am going to consider, this is I is equals to 1 to, this whole thing is by handshaking property, this I am taking it as even number. So whenever if it is even, so here I am going to take, this is a sum of even degree vertices. So this should be always even, whatever the number of vertices will be there, whether it is odd number of vertices or even number of vertices. If I am going to multiply odd or even with even number, I am going to get this is even. This is even. So finally, what I am going to get is I am going to take it as summation of I is equals to 1 to k degree of vi. This is odd degree vertices, and summation I is equals to k plus 1 to n and degree of vi, which is equals to, by using handshaking property, which is nothing but 2 into number of edges, so which is even number. So already this is even. This is even because we are considering only even degrees. So number of vertices, either it is even or odd, the total product should be even. So then if I am taking to this one, even minus even number, we are going to get even. We are going to get it as even. So now what about the sum of the vertices whose odd degree must be even? So when it is possible, whenever the number of vertices must be even, then only this is possible. Otherwise it is not possible. So k should be positive. K should be even number. If k is odd number, then odd number into odd degree, then I am going to get odd. But here I am getting this sum is, I am going to get summation I equals to 1 to k degree of vi. So must be even. When it is possible, whenever k is even, so even number into multiplied with odd number, then only I am going to get even. So k should be even. Means the number of vertices of odd degree must be even. So it is the proof of this is same. So in this way we are going to explain the proof of this. In every group, see here, in every graph, the number of odd degree vertices, because obviously it is a even number. Some of the degrees of vertices are even. So we are going to separate the number of vertices of odd degree and the number of vertices are even degree. So number of odd degree vertices I am taking 1 to k, and the remaining vertices degrees are even. So remaining degrees of vertices are even degree. So whatever the number of vertices, either it is odd number or even number, the product should be even. If I am taking that to that right hand side, that should be even. Even minus even is even. So it is nothing but odd number of this is summation I is equal to 1 to k degree of va is even. This is possible only if k is even. That is even number of degrees will be there. Even number of vertices will be there. Whose vertex degree is odd, then only it is possible we are going to get even. So we can say that the number of vertices of odd degree is even. Now let us go for some of the examples in this. See here, can be there a graph containing the vertices P, Q, R, S with this degree sequence. It is given like this. See sum of the degrees. What is the sum of the degrees I am going to take by using handshaking property? So what is the sum of the degrees? 2 plus 3 plus 2 plus 2. So which is equals to, so it is 6 plus 3, 9. 9 is not even. So there is no graph. Which this degree sequence. It is there is no graph containing this degree sequence because it is not satisfying handshaking property. That means if I am taking the sum of the degrees of all vertices, which is not even. So this degree sequence is not possible. Now, the another one is for a graph Z. What is the largest possible value for V if number of edges are given as 19 and the degree of each and every vertex is greater than or equals to 4? So what is the largest possible value that we have to calculate? largest possible value that we have to calculate. Let us consider the number of vertices. The number of vertices of this graph is, let G is having n number of vertices. Let G is having n number of vertices. Then it is given each and every vertex degree is greater than or equal to 4. Then what is the sum of the degrees of all vertices? Sum of the degrees of all vertices, or I am going to represent like this. So there are n vertices. Let those vertices are V1, V2 and so on Vn. Then I am going to take it as sum of the degrees of all vertices I is equals to 1 to n. So each and every vertex degree is 4. That means degree of V1 is greater than or equal to 4. Degree of V2 is greater than or equal to 4. And so on. Degree of Vn is greater than or equals to 4. So the sum is degree of V1 plus degree of V2 plus degree of Vn, which is greater than or equals to 4n. Which is greater than or equals to 4n. So then I am going to take it as which is greater than or equal to 4n. Which is greater than or equals to 4n. So now by using handshaking property, this is 2 into number of edges which is greater than or equals to 4n. So which is 4n is less than or equal to 2 number of edges. And how many edges it is having which is less than or equal to? So it is 2 into 19. So it is 38 edges. So it is 4n is less than or equal to 38 edges. N is less than or equal to 38 by 4. 38 by 4. So what is the what is given? What is the largest possible value? Largest possible value, that is it is less than 10, right? It is less than 10. Number of vertices should not be a fraction. It should be less than 10. Less than 10 means what is the largest possible number of vertices is? Only 9. So n should be equal to 9. N should be equal to 9. So the largest possible value of the graph is n is equals to 9. N is equals to 9. So this is the largest possible value. Now we are considering the other problem. Let us prove that hypercube Qn has this many edges. Now let us go for a hypercube. I'm just taking the hypercube Q3, a particular hypercube with 3 number of vertices. What is that? What is the shape of this? Is the hypercube I am going to consider. Let us take the hypercube is so this is a hypercube. So it is nothing but which is a 3 regular graph. It is a 3 regular graph. I am just taking which is a Q3, which is a Q3. So 3-dimensional hypercube and which is denoted by Q3. Now here observe that each and every vertex degree is 3. Each and every vertex degree, whatever the vertex is there in this, how many vertices are there? Then which is going to be 1 to 4 and 4, it is 8. How many vertices it is having? It is 8 vertices. Each and every vertex degree is 3. Each and every vertex degree is 3. So what is the sum of the vertices of degrees is nothing but 24 we are going to be. Okay, leave it. Now we are concentrating on this. It is a hypercube. If I am considering Q3, each and every vertex degree is 3. Each and every vertex degree is 3. let us, I'm just taking number of, this is how many Q3 if I am considering, this is 8, so which I am going to write it as 2 to the power of 3 vertices. 2 to the power of 3 vertices. Now, if I am going to consider any Qn, then how many vertices it is having? It is having the total number of vertices are, how many vertices it is having? 2 to the power of n vertices. 2 to the power of n vertices it is having. Each and every vertex degree, it is nothing but an n regular graph. Each vertex degree, here what is each and every vertex degree in Q3 is 3, in each and every vertex degree is n. Then the sum of the degrees of all vertices in Qn, which is nothing but sum of d of degrees of all vertices, I is equals to 1 to n, which is equals to, what I am going to take, n into 2 to the power of n. N into 2 to the power of n. So this is nothing but 2 into number of edges, which is equals to n into 2 to the power of n. Then number of edges are 1 by 2 into n into 2 to the power of n, which is nothing but n 2 to the power of n minus 1. So this is proof that the Qn has 2 to the power of n into 2 to the power of n minus 1 edges. So it is having these many edges. So Qn is having how many vertices? 2 to the power of n vertices. And how many edges it is having? Let us say the number of edges are cardinality of E, and each and every vertex degree is n. Then sum of the degrees of all vertices are, see what is that? Degree of V1. Let us say degree of V1 is 2 power n, degree of V2 is 2 power n, and degree of, and so on. Degree of Vn is also 2 power n. So if I am adding all the degrees, then it is n times it is repeated, n into 2 to the power of n. This I am going to write it as n into 2 to the power of n. So that's I am mentioning here. I am mentioned here. Then the number of edges in the hypercube Qn is equals to this. Now, see, hence determine the number of edges in Q8. So just a number of edges in Q8, n is equals to 8. I am taking it as a particular case, Q8. So n I am taking the 8, then which is equals to 8 into 2 to the power of 8 minus 1. So 8 into 2 to the power of 7. So these many edges, a hypercube Q8 it is having. Q8 it is having. So like this we can solve the problems. So completely, which is based on the handshaking properties. Now here, let us, which is related to the same previous result. And what is the dimension? What is the dimension of the hypercube with these many edges? With these many edges. So here it is given, that is what is the dimensions that we are going to calculate. So here then what is how many hypercube? Let us say it is having k hypercube, each and every vertex degree is k. Then what is this here? This in the based on the previous one. So what I am taking, k into 2 to the power of qk. Let us, I am going to consider qk hypercube qk. Then we are going to consider, let us take this as, let the hypercube is qk. Then each and every vertex degree is each and vertex degree is k, and there are, let us say, k vertices. Then sum of the degrees of all vertices, so which is nothing but k into, see how many edges it is having. So it is having k into 2 power k or n into 2 power n minus 1, whatever the way that we are going to consider, k into 2 power k minus 1. It is already given these many edges. So it is 5, 2, 4, 8. So we are going to find the factors for this. 5, 2, 4, 8, 8. Just I am taking like this. 2 factors I am finding. So 2 4s, 2 6s, 2 2s, then 2 4s, 2 4s. Like that I am going to calculate the factors. 2 3s, then 2 1, 2 2, 2 2. Like that I am going to calculate. Then we are going to get, this is 2 to the power of 19 times. 2 to the power of 19 times. So 1, then 1, and then 5, then 6, then like this you have to calculate all the things. Then we are going to get, so it is a 2 2s, then it is 2 3s, 2 1s, 2 2s, 2 2s. Like that, just to calculate 2 to the power of 19, it will become the equivalent value is that. So this I am going to write it as 2 to the power of 4, and I am going to express in this form 2 to the power of 15. 2 to the power of 4 is nothing but 16. 2 to the power of 15. 2 to the power of 4 is nothing but, just I am taking into 2 to the power of 15. So it is nothing but, if I am taking, just comparing, just k to the power of minus 1. So which is a k, and then this is a 16, and 2 to the power of 16 minus 1. So from this I can say that k is equals to 16. What is the dimension? This is nothing but the 16. So I'm going to calculate what is the k. The dimension is, I'm taking it as k, and k is equals to 16. It is nothing but just we are going to find the order. Now let us go for the another one in the same way. So B is, how many vertices are there in the hypercube? Edges are given. How many vertices? Let the number of vertices. In the same way I am taking, let the number of vertices are n. Then what I am taking? 2. The term of the degrees of all vertices is n, 2 to the power of n minus 1 is equals to 4, 9, 8, 0, 7, 3, 6 edges. And once again, this will be the same, that we are going to write it as 19 into 2 to the power of 18. Just by using factors. If it is not exactly, I am not going to get some other number, I am going to get like this. So I am going to compare this. Then it is nothing but, just by comparing this, n is equals to 19. Number of vertices are 19. Just comparing. If it is factors directly, we are going to able to find out like this, then we can do that. If it is not possible sometimes, and whatever the constants will be there, that constant is equal to k or n, whatever the number that we are going to choose. And here the power is, we are going to express this number minus 1. Subsequently, we are going to find now how many number of vertices will be there, how many number of vertices are there in the hypercube with these many edges. So these are some of the problems which are related to the handshaking property, and we are going to continue handshaking property in the next session also. With this, I am going to conclude this. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.